Today we're starting with an introduction to proof. But before we even start and try to prove something, we first want to get familiar with some of the terminology that we'll be using in proofs. So to start, we want to look at the real number system. So these are the sets of numbers that we can pick that are commonly used. So the set of real numbers, which is denoted as R boldface, which is an R with two lines on the left, consists of all the numbers that can be thought of as points on a number line. So if you can place it somewhere in this one-dimensional plane, then it is a real number. So that includes numbers like 1, -1, a million, -a million, 0.635 recurring, pi. If I can place it somewhere, if it has a value to it, then it's going to be a real number. Now, a smaller set than the real numbers is the set of natural numbers. So natural numbers are our counting numbers. It's denoted as boldface n, which is an n with two lines on the left. That's numbers like 1, 2, 3, 4, 5, 6, so on and so forth. The set of integers, where n is equal to the set of sort of 1, 2, 3, and so on. So that's our set. The set of integers, which is denoted as bold-faced z, which is a z with two lines on the diagonal, consists of all the positive and negative natural numbers and 0, which is neither positive nor negative. So z would be equal to, and we want to choose how we define this very carefully, because we don't want it to be going on infinitely in both directions. We just want it to be going infinitely to the right. So we actually start with 0, then we get 1 and -1, we get 2 and -2, and then that pattern will continue on forever. So we've chosen it in a way where we don't have dots either side. So z positive would be 1, 2, 3, and so on, and z negative would be -1, -2, -3, so on. So using set notation, z is the union of the positive integers, the negative integers, and the set containing 0. So we're then looking for the types of numbers that are defined as being ratios of two integers. So that root word of ratio we turn into the word rational. So you have to have an integer on the numerator and an integer on the denominator. So a and b can't have any common factors except 1. If they did, then we'd be able to make the fraction simpler, which we would absolutely do. So they can't have any common factors. It's considered always in its simplest form. And then, of course, b can't be equal to 0 because we don't know how to divide by 0. The set of rational numbers is represented by, it's a Q that's boldface, so it's like a Q, but then it's got a diagonal across the circle on the Q. And then we call it Q is equal to A on B, A element of integers, B element of integers, and then we say that the greatest common divisor of A and B is equal to 1. So we can see having those two numbers in a bracket in set notation means that the common divisor of A and B is 1. Integers are what we call a subset of rational numbers. So all of the integers are located in the bigger set of ratios, since that's just the same as letting b equal 1. So if we let b equal 1, then all of a sudden integers are just the numerators, and we know that a is an integer, we know that b is an integer, so if we set b equal to 1, then we get the set of all rational numbers. So some examples of these. We have terminating decimals, so that's something like a half, which is just 0.5. That's something like an eighth, which is 0.125. That's even something like -9/5, which is -1.8. On the other hand, we have recurring decimals. So 1/3, would be the one that we're most familiar with, and that's going to be 0.333 recurring, which we denote as 0.3 with a dot over it. This is like primary school stuff that we're revisiting. If it's something like 7/11ths, that's going to be 0.63 recurring, which we write as 0.63 with a dot on either of them, or we can also write that as a line over the two numbers that are repeating. Or it might be something like 15/7ths, which actually has 6 repeating numbers. So this ends up being 2.142857 recurring. Right. So any real numbers that are not rational numbers are irrational numbers. So irrational numbers are denoted as the real numbers that aren't rational numbers. So we call this R without Q. So real excluding the set of rational numbers. So these include surds. So they're your root 2, root 10, and all other decimals that neither terminate nor recur. So examples of this, you've got root 5, negative root 18, pi, e. We can see they can be placed on the real number line, but they can't be expressed as a fraction. So in summary, we start with the real numbers, then we have the irrational numbers and the rational numbers. The rational numbers can be split into the integers and the non-integer rationals. And then the integers have the negative integers, the zeros, and the positive integers, which is your natural numbers. So, rational or irrational. If a number can be expressed as a whole number, a fraction, or a terminating or recurring decimal, it is rational. If not, then it is irrational. So for example 1, identify the following numbers as either rational or irrational. Starting off with A, number 7. Very simple to start off with. 7 is a whole number, so it is definitely an element of the rationals. Part B. Now it's trying to trick you here because it's got a square root symbol, but our numerator and our denominator are both squares. So taking the square root of that, this is the same as just 5 on 7. Now 5 on 7 is a fraction, so that is rational. Part C, we have 0.25. Now 0.25 is just 25 over 100, which if we divide both, we can see is a quarter. That is definitely rational because it's 1 over 4. For part D, this is where it gets a little bit tricky. So this is a series of decimal points where the decimal place is changing each time. So it starts with 0, 1, then it goes to 0, 1, 1, then it goes to 0, 1, 1, 1, and then it would go to 0, 1, 1, 1, 1. Now, this is not terminating, and this is not repeating, because it never repeats itself. It starts increasing the distance between zeros. So this is not recurring nor terminating. Which makes this, so 0.010110, etc., is going to be an element of, and just a reminder for this, it's R, so R without Q. Part E, 3.77 recurring. That can be expressed as 3 7/9, so it is rational. And then part F, we've got root 5. We know surds is irrational, so that's going to be an element of the reals without the rationals or the irrationals. And then lastly, 2 times pi, which is already irrational, is definitely going to be irrational. So 2 pi is also an element of the reals without the rationals, so the irrationals. Okay. Converting between decimals and fractions. So we're going to jump back in time a little bit to back when we were in junior school and first learning how division works. And we're going to apply our division algorithm here. So if I were to divide 1 by 50, I've got 50 outside the bus stop and I've got 1 inside the bus stop. And I'm going to add all of these zeros to it to help me in there. So 50 goes into 1, no time, so we go to the next set. 50 goes into 100 twice. So our answer here is going to be 0.02. Now for part B, we've got 7 being divided by 9. So 9 goes into 70, 7 times. We have a remainder of 7. 9 goes into 70 7 times with a remainder of 7. So we can see this is recurring forever. So that's going to be 0.77 recurring. Part C, 5 into 11. So we're dividing 5 by 11. I'm just going to remind myself how many decimal places this goes to. Just 3. Okay. So 11 goes into 50. 4 times, that's going to get us to 44, and we have 6 left. So 6 becomes our remainder. I'm doing short division here. Apologies if you're more used to the long division. So 11 goes into 60 then 5 times, and we're going to get to, therefore, 55, but we're going to be 5 short of 60. So our remainder is 5, and we can see our remainder gets us back to where we were to begin with. We're now finding 11 into 50, so this is going to keep going. So this becomes 0.45 recurring. For example 3, we want to take these recurring decimals and convert them back into fractions. So we have an interesting way of doing this using algebra. So what we're going to do is first, let x equal our recurring decimal. We now need to turn this into a fraction. So what we want to do is subtract this x away from something that shares the exact same recurring part. So how are we going to do that? Well, we need to move this decimal point 1 place down. If we do that, our repeating part is preserved. It's still 0.222 forever. So if I take 10x, we're going to get 2.2222 forever. Now you can see if I take away x from 10x, I'm going to get 9x. So this is 10x take x is equal to 9x, which is going to be equal to 2. So x is equal to 2/9. Similar process for part B, but now we need to think how much do I need to multiply it by to preserve that recurring decimal part. So 215, 215, 215. We're letting x equal that. Just let me tidy this up. Okay, so letting x equal that. We then need to move the decimal 1, 2, 3 places. If we move it 3 places, then it's going to preserve the repeating pattern. So we want 1000x. So 1000x is equal to 3215.215 recurring. So same process. We do 1000x, take x is equal to, so we get 3215 take 3, which is 3212. Sorry, let me just check something. My apologies. It seems I was reading the question wrong. So it's not 3.215 recurring. It's just 3.2 and then 15 recurring after. So I'm just going to fix this up and I'll be right back. Okay, that's looking a little bit better. So we let x equal 3.2151515, so on and so forth. Now we need to first of all, make this so that we're just having the recurring decimal. So to just have the recurring decimal, we want this to be 10x, which is 32.1515, so on and so forth. Now we need to think, what do we need to multiply 10x by to preserve the recurring aspect of it? So we need to multiply it by 100. So that gives us 1000x, which is equal to 3215.1515 recurring. Now if we subtract them, we're going to get 990x is equal to 3215 take 32, which is 3183. So x is equal to 3183 over 990. In our denominator, 990 is a multiple of 3, and 3183 all adds up to be a multiple of 3. So these share a factor of 3. So this is actually 1061 divided by 330. So we can say that 3.215 recurring is equal to 1061 divided by 330. If we wanted that as a mixed fraction, that would be 3 and 71 330ths. And that is all for this video. Thank you very much.